let's turn our attention to circular motion. And we're going to be talking about uniform circular motion, which means that you're traveling at a constant speed and there's no friction in it. So you just stay moving around the circle at the same speed. We're going to make sure that you understand that because we're traveling at a constant speed, it does not mean that we're traveling at a constant velocity. It means that we are changing our velocity because every instant in time, we are moving in a different direction. So we might be traveling around the circle at 50 miles per hour, but every instant we have a different direction. So our velocity is changing, which means there has to be a net force acting on us. And it turns out that that net force is always going to be acting towards the center, and we call that centripetal force. However, when you experience this, you may feel like you're being pushed outward. So imagine going around a curve on a road. As you go around that curve, you may feel like you're being pulled outward, but think about what's really happening. At every instant, you are trying to go in a line tangent in whatever your current state of motion is because of your inertia. And instead of doing that, the car is actually moving underneath you. And so you kind of ram up against the side of the car, the outside of the car, or the outside of the circle. And what's keeping you on the road is the friction between the road and the tires. And it's pushing the car inward, keeping it from moving in that line tangent to the circle at every instant. So you would like to move at a line tangent, but you can't because there's this inward force always pushing you inward, and that is centripetal force. That feeling of being pushed around, the being pushed outward is a false sense. It's called centrifugal force, and it's not really happening. It's really your inertia, or tendency to go in a line straight at that instant. So that velocity that you are traveling at, its tangential velocity, is really equal to the distance around the circle divided by the time it takes to go around the circle. The time for one complete rotation is called the period of rotation, and its symbol is capital T. It's measured in seconds. And the distance is just the circumference, 2 pi r, around the circle. So if you know the radius in meters, you know how long it takes you to go around that circle, you can figure out what that constant tangential speed is. 2 pi r all over t. So if we took an example of a 50 kilogram mass that makes 6 rotations in a minute, and as it swung around in a circle of radius 1 meter, if we wanted to find its tangential velocity, first let's find its period. Its period is how many seconds it takes for one rotation. Well, we know that it takes 1 minute or 60 seconds for 6 rotations. So one rotation is 10 seconds long. And the tangential speed is just 2 pi r all over t. And r in this case is 1 meter. So 2 pi times 1 meter divided by 10 seconds is going to be 2 pi all over 10 meters per second. And in physics, we usually multiply that out. And we use our pi button. So I'm just going to say 2 times. And I'm going to find the pi button if there is one on this calculator. Let's see if we can find it. Oh, there it is. 2 pi. So, okay, let's clear everything. 2 times pi times 1 equals, divided by 10 equals 1.26 meters per second. So this object, if I were to draw its circle, has a radius of 1 meter, and its velocity as it rotates around is 1.26 meters per second every instant in time. So if it's accelerating, which way is it accelerating? Well, think about it. If it's rotating around clockwise, when it's right here, it wants to go straight up. And a minute later, it wants to go this way. So what has happened is that this velocity has been pushed towards the center, and so it is experiencing centripetal acceleration. It turns out that centripetal acceleration is equal to v squared all over r. So if you know what the tangential speed is, and you know r, then you can find the centripetal acceleration. So in our last problem, v was 1.26 meters per second, and the radius was 1 meter. So this object has a centripetal acceleration of 1.26 meters per second squared divided by 1 meter. And so that would be, if we put it in our calculator, 1.26 squared divided by 1 is 1.58 meters per second squared. Let's try another one. So if we wanted to find its we have a 1,000 kilogram car rounding a quarter at 60 miles per hour. I'm going to do a quick conversion because my speed needs to be in meters per second. And 1 mile per hour is 0.447 meters per second. So 60 times 0.447 is 26.8 meters per second. My acceleration is v squared all over r, which is 26.8 meters per second squared, divided by a radius of 10 meters. So in my calculator, I'm just going to put 26.8 squared and divide it by 10. And that's an acceleration of 71.8 meters per second squared. I wanted to show those vectors, right? Let's say it's rotating around this way. And this is r. So at this point, the velocity vector goes this way, and the acceleration vector is this way. So centripetal force is the force that's providing that acceleration. And remember that force equals ma. So in this case, a is v squared all over r, so centripetal force is mv squared over r. Notice that as the radius increases, FC is inversely proportional to AC, to R. So if R goes up, FC will do the opposite. It will decrease. But it's directly related to V squared. So if the speed increases, FC will increase, and specifically, it's directly related to the square. So if I double the speed, the centripetal force will be 4 times bigger. If I triple the speed, the centripetal force will be 9 times bigger. So it really makes a big difference when you speed up, how much force you feel. So let's talk about the centripetal force that was acting on that car. So we found earlier that the centripetal acceleration was 71.8 meters per second squared. So F equals MAC. M is 1,000 kilograms, and this was 71.8 meters per second squared. So the centripetal force would be 71800 newtons. If I want to show a vector diagram showing all the forces and velocities, so here's the radius. You would have a velocity, it would have an acceleration, and it would have a centripetal force. So these are all the vectors representing the velocity, the acceleration, and the centripetal force. Over here, the centripetal force would still be towards the center. The acceleration would still be towards the center, and it would be moving in a line tangent to the curve.